Hello everyone. Today we are starting our 2016 webinar series, and we have the pleasure to receive Professor Roy Maartens from the University of Western Cape in South Africa and the University of Portsmouth and in UK. And so he's going to tell us about the SKA and what can be done in cosmology with it. So very happy to receive you, Roy. Thank you very much for accepting the invitation.
Thank you very much, Vinicius, for inviting me, and hello to everybody, friends and others I don't know in Brazil. I'd rather be there, but this is second best. So I want to talk today about the kinds of cosmological science we could hope to do with the Square Kilometre Array. As you know, that is being mainly constructed in South Africa, and I have quite a strong link to the project here in South Africa, and that's the reason that I'm so interested in it. But it's not just that, it's also because cosmology with the SKA coincides with some of the topics I'm most interested in. So in this talk I'll try and show to you what special properties of an SKA survey we have that we can exploit to do either old cosmology, maybe better, and also some new cosmology. So I wanted to start off by saying that, in a sense, the cosmic microwave background was the frontier of cosmology in previous decades, giving us the real core of precision cosmology. But we're in a transition period where galaxy surveys are, in a sense, taking over. And I'd say that huge galaxy surveys are the next frontier of cosmology. The CMB remains important, but we're not going to get orders of magnitude improvements in CMB experiments. On the contrary, in galaxy surveys, we will be looking at huge improvements over the next few decades. And the current state-of-the-art spectroscopic survey is the BOSS survey, which covers nearly 10,000 square degrees. It's in a reasonable redshift range. DES is also operating at the moment. That's a photometric survey, so it's weak lensing, and the BOSS is the Baryon Acoustic oscillations. That's the state of the art at the moment. And they both, the BOSS has delivered fantastic science, and DES will deliver, I'm sure, also fantastic science in the coming months and years. But there's a new generation of surveys, some currently under construction and others still in the planning stage. In particular, the Square Kilometre Array, the Euclid satellites, the LSST ground-based satellite, and others. And these surveys many of them are characterized by delivering a much greater volume than current surveys, and therefore greater precision. The other thing about the greater volume is that these surveys will be able to access larger scales than we have been able to up to now. So before I come back to the scientific issues in general, let me just say something specific about the SKA. The SKA is being built in two phases, and phase one has been re-baselined. This is a fancy word for saying it was cut, because the amount of money available in the first phase was less than expected. So in this slide, which is slide number 3, I think, I'm showing what SKA Phase 1 looked like before the rebaselining. This was, say, 2014 and early 2015. The idea was that there'd be 2 sites, South Africa and Australia, and 3 observatories or telescopes, 1 in South Africa and 2 in Australia. So the one in South Africa was called SKA mid-frequency dishes, and it was going to be 190 dishes plus the 64 Pathfinder dishes from South Africa called Meerkat. The 2 Australian-based surveys were SKA survey, which was also a dish survey with 60 dishes plus the 36 ASCAP Pathfinder dishes, and then SKA low frequency dipole array, 250,000 of them. So that's what it looked like, and construction from 2017 to 23, and after 23, phase 2 would begin.
Sorry, Roy,
So,
you're only seeing slide number 1, only the title.
so I don't know what's going on because I'm seeing slide 3.
Maybe if you can turn off and turn on again the screen, share screen.
Okay. So I'll go back into Adobe, View, full screen mode. So you see slide 1 now. Do you see slide 2?
No.
Oh dear.
So maybe turn off the...
Should I go into not...
Maybe turn off the screen share and turn on again.
All right, so turn off the screen share.
Oh.
Stop sharing my webcam, not that one.
No.
Screen share. I don't see where the option is to turn it off. Is it one of these? Can you see where my arrow is going?
So in that top bar, there is a microphone, a screen, and a camera. So that the screen should be gray, and if you click...
Okay, so I've just got a message. I have been made the presenter.
Yep.
Show my screen or not yet?
Yes, sure.
So should I say click show my screen?
Yes.
Okay. Now you see it?
Yes.
We do.
Okay, let's try the PDF. No, that's the webcams. No. Sorry, I'm not doing very well here, but let me see. Full screen mode. You see slide 1?
Yes.
2?
Yes.
Yes.
I see it now.
Oh, okay. So. Yeah.
Okay, sorry. And you don't see the go-to control panel?
No.
Okay, that's what I'm seeing, so that's okay. All right, so let me just quickly go back to screen slide 2, where I was just talking about galaxy surveys as the next frontier, and I showed the boss sky coverage there. So then moving on to slide 3, I've been talking about what the SKA Phase 1 looked like before the rebaselining. And the rebaselining was forced by having less money than was expected. So as I said, the 3 parts of the SKA 1, 2 in Australia and 1 in South Africa, they looked, as in the slide, you could see 190 plus 64 dishes for SKA mid, 60 plus 36 for SKA survey, and 250,000 dipoles for SKA low frequency. And the rebaselining forced us to cut back. So for SKA mid, instead of 190 extra dishes, there'd be 133 in phase 1. SKA survey has been deferred to phase 2. And SKA low is getting half the number of dipoles, 125,000. So this is what the SKA looks like up until 2023, with early science expected in 2020, so it's not that far off. Phase 2 of the SKA will be from 2023 to about 2030, and that is when the total collecting area of the SKA is supposed to add up to 1 square kilometre. By the way, please interrupt me at any point. Since I can't see the audience, I'm not sure whether what I'm saying is connecting or not, so I'm quite happy to be interrupted. So that's the general description of the SKA. This slide, the next slide, which I think is number 4, shows 2 of the 64 meerkat dishes. I think there are now 8 or 9 already up. So it's quite a nice photograph because the South African site is set in a semi-desert area which has these beautiful sunsets and sunrises because it's very dry and dusty. And so some of these night shots are really quite beautiful. And you can see also the size of these meerkat dishes. There'll be 64 of them by the end of 2017. And early science will start by the end of this year. So already we'll be doing early Pathfinder science in South Africa in the next year. So let's go back now to the question of cosmology with the SKA, the next slide. The next few slides I'm going to just summarize what are the cosmological surveys that will be done in the radio wavelengths by the Square Kilometre Array. There are 3 types of survey. If you think about optical and infrared surveys that we know, they're generally 2 types. They're either spectroscopic or photometric. In the radio, we have 3 types. The first one is the one that's most like a spectroscopic optical survey. And this is a neutral hydrogen, or H1, galaxy redshift survey. So we have this feature of neutral hydrogen that it has a spin-flip transition shown in the diagram in the white box. And this transition occurs because when the electron spin is anti-aligned with the proton spin in the hydrogen atom, you're at a slightly lower energy state than when the spins are aligned. And so when the spin flips from up to down, a photon is released carrying away that excess energy, and that's in the rest frame of the hydrogen atoms, that's 21 centimeters or 1420 megahertz frequency. So this is a very weak transition. It only is possible to detect it because there's a huge amount of hydrogen in the universe. So this H1 transition can be detected even before the first stars form, in principle, in the dark ages. It's the basis of the epoch of reionization experiments, but I'm now talking about after the EOR, when galaxies have formed. Those galaxies which contain neutral hydrogen, we can call them H1 galaxies, will be emitting this 21 centimeter radiation in their rest frame. And when you detect a galaxy in neutral hydrogen, you immediately, as soon as you detect it, you have its redshift to extremely high accuracy. So unlike an optical survey where generally you use imaging or another photometric survey and then you follow up with your spectroscopy, in this radio survey you get spectroscopy immediately with detection. There are no foregrounds to worry about because the detection of the galaxy is a detection. You don't worry about foregrounds in this case. No contamination from stars as you would have in optical surveys. The stars do not emit 21 centimeter. The catch, though, the but here, is that we need extremely high sensitivity. So I'll come back to what we can do with the H1 redshift surveys a little later. Now let me move on to the second type of survey, which is a slight change to the previous one in the sense that we don't resolve individual H1 galaxies. We simply detect the integrated unresolved emission of H1. So this is a bit like doing the CMB, but you can do it at any redshift by just tuning your frequency. And in fact, it's not a problem that we don't detect individual galaxies, because for large-scale cosmology, for example, Baryon acoustic oscillations, retrospace distortions in the linear regime, and primordial non-Gaussianity especially, you don't need individual galaxies, you just need the fluctuations on large scales. So although we don't count galaxies, we have exquisitely accurate redshifts. So we have a weakened angular resolution, but we maintain the radial resolution. Going out in the radial direction is going out in the redshift direction. So in principle, you've got the CMB, like the CMB, but doing the galaxy distribution tomographically. And this would mainly be done for cosmology via single-dish autocorrelations, not interferometry, because the autocorrelations of single dishes gives you a much wider field of view. So you need to survey large areas of the sky. This is the way to go. But here the big catch is foregrounds. So because you're not relying on individual detection, you're not sure whether your unresolved signal, your integrated signal, contains foregrounds noise in it, a foreground contamination in it, and it does. And in fact, these foregrounds grow stronger the further back you go in redshift. The epoch of reionization experiments are based on intensity mapping. It's just that they're not looking at galaxies, they're looking at the ionized bubbles and the neutral in between. So foregrounds are a major problem, very much like the CMB. It's the same issue in the CMB, and although you have to do a lot of work to deal with foregrounds, that science of foreground analysis is well established from the CMB, and a lot of that can be taken over into radio cosmology with H1 galaxies. So the final and third type of survey in the radio is called a radio continuum survey. So in these surveys, individual galaxies are detected not through their H1 emission, but by their total emission, which is dominated by synchrotron radiation. So for example, AGNs and other type, and quasars and so on, are strong radio sources, or some of them are strong radio sources. The problem here, you see, each survey has a catch. The catch for this survey is that you don't get redshift information. So there are no spectral features like for the H1. I mean, the H1 is sitting in this signal, but it's completely drowned out by other signals like synchrotron. So if you look at the simulated number densities in the plot on the slide, radio continuum survey slide, you can see that even out to redshift 5, there's still considerable numbers of galaxies. These radio galaxies are like beacons. They're very powerful even out to high redshifts. And so there's great potential here because you're getting such a high number of galaxies in principle. But if you want to do certain science with this, you need some redshift information, and for this you need either optical partners or H1. If you can get an H1 survey in the same area, you can do some cross-matching to get redshifts from your continuum. Okay, so that's the brief summary of the three types of survey. For cosmology, we can actually use all three of them to do interesting cosmological science. And moving to the next slide, I'll start that discussion. What science can we do with these kinds of surveys? So let's just take a step back and ask about the science questions in cosmology that large galaxy surveys are well placed to tackle. I suppose the number one question would usually be, is dark energy the vacuum energy lambda, or is it some other kind of dynamical dark energy field? And usually what we do there is we parameterize the equation of state W of dark energy in that standard parameterization in terms of two parameters, W0 and WA. And that actually captures the behavior of lots of different kinds of dynamical dark energy models. And it also gives you a way of testing whether observations tell us that W is deviating significantly from -1, which is the value for lambda. Then we can also go beyond the question of dark energy, and we can ask, maybe, is there no dark energy? Is dark energy like an illusion? And we're measuring acceleration of the universe, not because of dark energy, but because Einstein's theory is breaking down on large scales. So this is the alternative, which is called modified gravity, the modification of general relativity. So we can also go beyond just testing lambda to testing GR itself by looking at certain kinds of observations, which I'll come to soon. A third major question that large volume surveys can help us to answer is whether or not the primordial spectrum of perturbations from inflation is Gaussian or non-Gaussian. And this is a very important discriminator between different kinds of inflation models. The simplest inflation models would have no primordial non-Gaussianity. And later on I'll discuss how galaxy surveys can, in principle, go beyond what the CMB has been able to do in terms of constraining the level of primordial non-Gaussianity. And there are many other questions. I haven't got them all here. I've just identified the ones I'm going to talk about today. The last one I have here is the question whether the large-scale structure of matter is isotropic like the CMB. So once you've removed the dipole of the CMB, you have a nearly very close to isotropic distribution over the sky. And if we are living in a standard Friedmann universe, then that should be the same for the matter distribution, for galaxies and other kinds of matter that we can measure. So the kinds of probes that we use in cosmology, whether it's radio or optical, to answer these questions would be the Baryon Acoustic oscillations, which give us the best probe of the expansion history of the universe. The Retrospace distortions, which give us one of the best probes of the growth rate of structure. There is, of course, weak lensing, but I'm not going to discuss it because I'm not going into that today. Both of those things require you to extract information from the power spectrum, but in order to go beyond just the BAO and the RSD, which are not good enough, for example, to measure primordial non-Gaussianity, then we also need to look at the whole power spectrum. And for that, the best option is to look at the full angular power spectrum with autocorrelations at fixed redshift and cross-correlations between redshift bins. So if there are no questions about that, I'm assuming, everybody, that my slides are now moving. Is that correct?
Yes.
Canisius?
Yes.
Ah.
Yes.
Okay. So please, as I said, please feel free to interrupt me. So these are the general questions, some of the general questions. Now let's take a look at how the BAO and the RSD help us to probe some of those questions. So the Baryon Acoustic Oscillation Scale, as this cartoon shows, is a scale that's imprinted in the galaxy distribution by the evolution of perturbations during the plasma phase of the universe and as it ended at decoupling or loss scattering. So the plasma, the acoustic waves before decoupling stalled at the time of decoupling, and essentially the distance that they had traveled from the start of the universe up to the time of stalling led to a slight overdensity on scales, on co-moving scale RS, the Baryon Acoustic scale RS, which we see in the CMB, but that slight imprinting on top of the primordial power spectrum of radiation is also carried through into matter. And so in the galaxy distribution, that same scale is imprinted. The question is, how do you actually extract it? So the Baryon acoustic oscillations are three-dimensional spheres within the galaxy distribution if we ignore redshift space distortions in real space. And in the radial direction, the extent of the Baryon acoustic sphere is a measure of the Hubble rate, as you can see in the white box on the right of the screen. And in the transverse direction, across the sky, the size of the sphere is given by the angular diameter distance. So if we can measure these spheres statistically, we know what the theoretical prediction is for the co-moving scale RS, and so we can start looking at correlations on scales corresponding to the BAO scale to detect the excess density around random galaxies in spheres of the radius given by the acoustic scale. So we measure the angular size and we measure the radial extent of the sphere statistically, and then from that we can deduce angular diameter distance and the Hubble rate. And the most recent data from the BOSS survey has been able to detect these two scales, the radial and transverse, separately, but still the statistics are not that good. But certainly with future surveys, it will be practical to detect independently both scales rather than just detecting an average over the two. So this next slide here just shows the Baryon acoustic scale in the CMB and at the corresponding position in the galaxy correlation function. So in principle, in galaxies, we would look at the correlation function in some form or another, either through real space or through the power spectrum, and pick up that bump and so detect the BAO. Redshift space distortions take into account the fact that we don't observe galaxies in real space, we observe them only in redshift space. And because they have peculiar velocities, they're falling into overdensities and are moving away from underdensities. This creates a perturbation on the Hubble velocity. And so in that cartoon, you can see that a sphere of galaxies in real space is rendered for an overdensity as a squashed ellipse, squashed along the line of sight. And for an underdensity, it would be an elongated ellipse, elongated along the line of sight. So we see a distorted view of the universe because we observe in redshift space. But that seems to be a problem, but actually instead of being a problem, it's giving us extra information. So if we can measure the monopole and the quadrupole of the observed power spectrum, we can then get extra information from the knowledge that we have of the velocities that cause this effect, because the velocities are closely linked into the overdensities that we measure in the power spectrum. So this is done using the Kaiser formula, so that the galaxy overdensity, whether it's radio or optical, it doesn't matter, the observed galaxy overdensity in redshift space is not just the bias times the matter, cold dark matter overdensity. It's corrected by a term f mu squared, where mu is the cosine of the angle between the Fourier mode and the line of sight, and f is the growth rate of dark matter perturbations, the logarithmic growth rate. So in principle, we can extract that f by measuring the monopole and the quadrupole of the power spectrum. And this growth rate f is a good diagnostic of deviations from lambda, but even better of deviations from general relativity. And typically just like we parameterize the equation of state of dark energy W, there's also a simple parameterization for the growth rate F. In a lambda CDM model, the parameterization is that F can be written as omega matter at conformal time eta raised to the power gamma, some index gamma, the growth index. In a lambda CDM model, both F and eta are independent of scale, so they're just, F and gamma are independent of scale, K. And in fact, gamma is pretty much equal to 0.55 for lambda CDM and also for dynamical dark energy, where the clustering of dark energy is very weak and can be neglected. So actually that means it's not such a good diagnostic on its own for dynamical dark energy, but it is a very good diagnostic for deviations from general relativity. So if we use retrospace distortions to measure the growth rate and use this parameterization, we can detect, if we can detect a large deviation from 0.55, that could be a signal of modified gravity. But of course, you'd also need to check the background evolution to see whether that was also giving you any information. So let me move now, having discussed baryon acoustic oscillations and retrospace distortions, let's now go back to the SKA and look at the three surveys that I've already described in general. What could they do? There's a series of slides that follows now showing some forecasts using simulations and forecasting methodology, exactly as you would do for a galaxy survey like Euclid or LSST. So if we look at the H1 galaxy redshift survey in SKA1, the first phase, the simulations show that around about 10 million galaxies should be detected spectroscopically, optimally over about 5,000 square degrees, so smaller than the Boss footprint, with a redshift round about up to 0.6, peaking at lower redshift. So that doesn't look in itself like it's going to outcompete Boss, but actually it does outcompete Boss at low redshifts, where Boss does not do too well. It won't be a game changer, this galaxy redshift survey in the first phase, but it will be another way of doing a spectroscopic survey with completely different systematics from the optical surveys that we're used to. And as I mentioned, because we get a high number of galaxies at low redshifts, it will produce the best constraints from galaxy surveys, at least in the phase 1, until Euclid comes online. In fact, Euclid won't cover these redshifts either, so it will actually produce the best constraints until phase 2 at low redshifts. If you look at SKA2, the phase 2 galaxy redshift survey, this is the deluxe spectroscopic survey to beat all spectroscopic surveys, because it's forecast to detect spectroscopically 1 billion galaxies out to a redshift of about 2, over 30,000 square degrees of the sky. So there's no currently known galaxy survey that will be able to beat that, although of course something else might come up in the future. What the plot here on this slide is showing is SKA1 in 3 blue curves and SKA2 in the 3 red curves. The 3 variations are the standard simulation forecasts in the middle curves, and then the pessimistic case if the instrument isn't as good as the simulations suggest, and the optimistic case if the instrument is better. So you can just get an idea of the range of possibilities. That curve shows the number density as a function of redshift. The dotted lines tell us at what redshift the noise has become too high for us to make detections of the BAO at the BAO type scales. So basically the surveys are good up to where they cross the dotted lines. You can also see in the yellow curve the Euclid spectroscopic survey, which starts at about a redshift of 0.7 or so. And so you can see how the number densities for SKA1 are going to take us into a new regime, but SKA2, SKA1 is only going to help us at very low redshifts. The second kind of survey was the intensity mapping survey, where we don't detect individual galaxies but only integrated signals. So we can only look at fluctuations on scales above, say, 20, 50 or so megaparsecs. Now, the power of this method is that it's able to probe very large scales, because even in SKA1, instead of having 5,000 square degrees of the sky like you have in the galaxy redshift survey, for the intensity mapping survey, we can in principle go out to 30,000 square degrees if that's possible in terms of costs and time. And the plot here is showing you what the error over signal on the power spectrum is at a scale of 0.01 per megaparsec, co-moving wave number. This is a scale which corresponds to a scale larger than the turnover scale on the power spectrum. So it's a scale which has not yet been probed by current galaxy surveys like BOSS. So if you look there, you see that on those large scales, the signal to noise from SKA1 is better than it is for Euclid, the Euclid spectroscopic survey. So if you're only interested in large-scale fluctuations at very large scales, intensity mapping is the weapon of choice, so to speak. And now, before I go to the continuum survey, let me just show you a few slides to illustrate the volumes involved, especially the huge volume of SKA Phase 1 intensity mapping survey. So this plot here shows the co-moving distance versus redshift to give you an idea of the volume covered by SKA mid in Phase 1. And you can compare it to Euclid and LSST, which are roughly given by up to the dark green contour, and SDSS3, which is BOSS, and some DR release, I'm not sure which one, shown in blue. Alternatively, we can look at the volume in the second plot here, the volume of the different surveys against redshift. This is the volume in cubic gigaparsecs. And each curve shows a survey where the horizontal line shows the redshift reach, and the volume is the volume at the midpoint. So once again, SKA1 mid-intensity mapping survey would have by far the largest volume if it could cover the 30,000 square degrees. SKA2, the blue line, doesn't have anywhere near as much volume, but more than half anyway. And then you see Euclid, DESI, WFIRST, HETDEX, and BOSS. So one thing that we're really getting out of the radio is volume. And the final slide here just shows us the redshift reach of spectroscopic surveys. The colored ones are radio SKA ones, including the EOR SKA1 low, and the gray ones are optical or infrared. So in terms of detecting individual galaxies, the blue SKA2 one doesn't go as far, obviously, as HETDEX or WFIRST or even LSST isn't actually spectroscopic, so I wasn't quite right in saying spectroscopic. I see LSST is there. So that just gives you an idea of the coming surveys. And of course, one of the points I'll come back to towards the end is that it's not a question of competing between all of these surveys. It's actually the question that we should be looking at is how to combine them, because together they can do amazing things. So now I come to the third kind of survey, a continuum survey. Since the continuum survey doesn't have redshift information, one thing it can do for us is give us a huge number of galaxies in an angular correlation function. So just to give you an idea of the volume, there's 100 million galaxies from the simulations in SKA1 continuum survey doing the full sky that's available to us, 30,000 square degrees. In SKA2, that would go up to 2 billion galaxies. And the cartoon there just gives you a comparison with Euclid and Boss in terms of the volume. One on the right also shows the Hubble radius in co-moving distance space. The one on the left is in redshift. So what can you do with an angular correlation function with those kinds of numbers of galaxies when you've got that kind of sky coverage? Well, as I mentioned, one of the key tests of our standard model is going to be to show that the dipole of the matter distribution coincides with the dipole of the CMB. Because if that's not the case, then the standard model is not a sufficient description of the universe. Then we're living in a universe with something that breaks statistical isotropy. So this is a key test of the standard model. The NVSS all-sky radio surveys have been used to try and detect the dipole, but the number of galaxies is far too low, and so the error bars are huge. Current work shows that there's consistency in the direction with the CMB dipole direction, but the amplitude seems to be out. So if you look at that cartoon on the slide, you'll see that the directions are pretty similar, but the amplitude of the radio dipole is just too big. So this is probably a function of the fact that we just don't have enough galaxies in the NVSS. The angular correlation function for SKA will be much, much better. So in phase 1, we would be able to forecast, say, we'd be able to detect the dipole within 5 degrees and narrow that down to 1 degree in phase 2. So we'll be able to make a precision test of isotropy of the universe. And then, in fact, we might be able to go further and investigate whether the large-scale, the wide-angled anomalies in the CMB are repeated in the matter distribution, or whether they're just statistical accidents in the CMB. So I need to speed up just a little, sorry. See, it's 1:45. The following slides just show us the accuracy that we get on the BAO in the radial direction, first of all. So this is the error on the Hubble rate from the radial BAO, the fractional error. And you can see that again, the gray surveys are the spectroscopic optical Boss, Euclid, which is H alpha, and HETDEX. And the lower the curves are, the better they're doing. The smaller the error. You can see Boss is doing quite well. But Euclid obviously outperforms it. But you can also see how well the intensity mapping surveys are doing. Forecast to do a lot better than Boss. Obviously, they don't get to quite the accuracy and precision of Euclid. The SKA2, phase 2 spectroscopic survey is the best of all, the blue curve you've shown there. And also shown is detection of the BAO using SKA low in the pre-epoch of reionization universe at very high redshift. Well, not just the pre one, including the going down to reionization. So it doesn't do that well, but it's just interesting that you can use the EOR survey also to detect the BAO. And for the transverse direction, similarly, it's the same sort of pattern. SKA2 is the best, and the SKA1 intensity mapping ones do pretty well compared to Boss, for example, but not as well as Euclid as expected. Then if we ask about how well does SKA do using retrospace distortions to probe dark energy, the biggest contour that you see on this WAW0 plot corresponds to the current best constraints from Boss. Then the darker gray contour in the center of the yellow there, that corresponds to Euclid. The red and the yellow are the two different bands for the SKA1 intensity mapping survey. So for band 2, we're doing pretty much the same as well as Euclid. The green is SKA low, and the blue gives us the best constraints we could hope to get, which come from SKA 2. The other thing we can probe using RSD is general relativity itself. And so the next plot is showing gamma, the growth index, against W naught. So we're just assuming a constant equation of state parameter for the corresponding to the background evolution. The central dot there corresponds to lambda CDM. And again, you can see going down from BOSS, the outer gray, to the green, SKA low, to the yellow, which is SKA 1 mid, band 2, band 1, and then Euclid in the inner gray, SKA 1 intensity mapping band 2, and finally SKA 2 spectroscopic survey. So the errors really are coming down with Euclid and the SKA. And what I haven't shown here is what one might get by cross-correlating, say, Euclid and the SKA. Of course, you get better constraints then. So what you're seeing there from the blue contours is actually going to be smaller when we cross-correlate these things. So I'm going to end off by turning to the question of large scale. On the largest scales, what kind of things we can do. So what do we need to probe galaxy counts or intensity mapping on the largest scales? So we just have to quickly think about what we're actually measuring in galaxy surveys. We count the number of galaxies per pixel in a chosen direction n on the unit sphere, and at a redshift z, and both of these are within a solid angle, say d omega n, and a redshift bin dz. So how do we actually describe the fluctuations theoretically? So there are two things we have to do to start with if we want to include the larger scales. First of all, our definition of bias must be gauge invariant, and in order to do that we need to define the bias in the synchronous gauge, because that is the rest frame of dark matter and galaxies. And that is where the bias has to be defined if we want the definition to be a gauge invariant definition. So my first term on the right of the observed fluctuation delta obs is B times capital delta M, where capital delta is the co-moving density over density of dark matter. And then, of course, the second correction is the Kaiser correction for retrospace distortions. But in fact, these corrections are not the end of the story. We also have a lensing correction. We know that distant galaxies are magnified by the intervening matter. And in fact, the number density of galaxies subject to lensing is given by the unlensed number density in the background spacetime, say, divided by the magnification mu. And to lowest order, this is the unlensed number density times a factor 1 minus 2 kappa, where kappa is the lensing convergence. So kappa corresponds to integrating along the line of sight all the fluctuations from all the matter that lens the light rays reaching us from the galaxy at redshift z. So from that formula for Ng, remember that delta observed is based on the fluctuations in Ng as the first term. Going to the next slide, the yellow formula at the top is showing me that the delta observed is the first term, B delta matter, the second term, the Kaiser term, and now a new term, the lensing contribution to the galaxy number counts. So just to be very clear here, the effect of lensing in this case is to change the fluctuation in number counts. This is not like a weak lensing survey looking at shear or looking at magnitudes or sizes of galaxies. It's simply a theoretical analysis showing that the convergence comes in to the galaxy number density through the term minus 2 kappa. I have neglected magnification bias, which tells you about the properties of the luminosity function. That does affect that factor of 2 and changes it a bit. I haven't got time to go into that. So remember that the retrospace distortions allow us to effectively measure the peculiar velocities. They give that extra information, as you can see from the Kaiser term above. The lensing convergence in principle will allow us to measure the lensing potential, because kappa depends on phi plus psi, the lensing potential, from number counts, not from shapes or magnitudes, not from a lensing survey, but from a number count survey. So this is an interesting new possibility. But moving on there, actually, that's not the end of the story. We can think of other possible contributions. What about gravitational redshift? And if we think of the CMB, what about the Sachs-Wolf and integrated Sachs-Wolf effects? What about time delay effects? In fact, these terms are all present because we do observe galaxies on the past light cone, and so all the effects from null geodesics must come in to the number counts. The point is that all these additional terms, apart from the ones we've seen, the Kaiser term and the lensing term, these further terms are completely negligible except on horizon scales. And in order to derive those terms, I'm not going to do it, but one has to look at the cartoon on the left there. We have to now take account of the fact that the geodesics are bent. So we have to look at the perturbation in the actual position of the perturbation from the background position of the observed position in the of the galaxies. So when you do that, these effects have been computed by various people over the last few years, and I'm just going to show you the summary of the formula here. This is a nice cartoon that I've taken from Bonvin, but there's a slight notation change. So if you look at the top line there, what I've been calling delta obs, in the notation of Bonvin is capital delta. What I've been calling delta matter, the co-moving over density, and this new notation is capital D. And my radial co-moving distance chi is, in this case, R. So if you just think of those changes of notation, then having a look at the final formula here, the first term is the standard density term, which dominates, except on horizon scales. The second term is the Kaiser term, we know. The third is the lensing term we've just discussed. And then the next three lines are all the general relativistic terms coming from light cone-based observations. And they split into the first line, which are terms that have the size h over k times the density. And the second two lines, which grow as h over k all squared times the density. So you can see that those last three lines will completely dominate on horizon scales as you get close to the Hubble radius at the given redshift, and as you reach that radius and as you go beyond it, those terms are growing bigger and bigger and bigger. And they include terms that you would get in the CMB, but they're obviously in a different form here: Doppler terms, gravitational redshift, Sachs-Wolf type terms, integrated Sachs-Wolf, and Shapiro time delay terms as well. So the second slide just shows how I've split those things up. In fact, in the first slide, sorry, I was talking about the growth rate of the terms, and that's actually only shown on the next slide. Oops, that one. So this slide just has the same formulas, but is now identifying that the lensing is the term important at high redshift. For obvious reasons, you need a high redshift to accumulate the effect of lensing on your distant galaxies, or the image of your distant galaxies. Well, not the image, sorry, the number counts. And then the relativistic terms, the first line going like h over k times d, as I said, and the second two lines going like h over k squared. So we saw the new information in Kaiser term was the peculiar velocities, the new information in the lensing term was the lensing potential. Now you can see the new information in the GR contributions is the velocities and the potentials on large scales. The trouble is that these terms are significant exactly where cosmic variance is growing on very large scales. So at the same time, I just wanted to remind you that primordial non-Gaussianity is frozen into the galaxy distribution through a change in the galaxy bias And in the white box there, you can see that the Gaussian galaxy bias B is shifted by an amount delta B that is proportional to the non-Gaussian parameter FNL over K squared. So the effect of primordial non-Gaussianity on very large scales is to boost the power in the power spectrum. And that's how you try to measure it in galaxy surveys. But of course, cosmic variance is a huge problem there, and that's why the current constraints are very poor. So we've got two issues here. We can measure these GR effects, and we can measure FNL to high accuracy if we can deal with cosmic variance. And one can actually show that even the best versions of Euclid and SKA and any other surveys that are being talked about are actually unable to measure the GR effects and unable to get the error on FNL below 1. Currently, that error from the CMB from Planck is about 7.5. And that's using the large-scale structure convention. So how do we push below 1 and how do we detect these GR effects? Well, we have to use the multi-tracer method where we can beat down cosmic variance by using more than one tracer of the same matter distribution. The dark matter distribution can be traced by two different types of galaxies, possibly two different surveys. So for example, if I use a Euclid photometric survey and an H1 intensity mapping survey over the same area of the sky in the same redshift range, then I'm sampling the same stochastic distribution of dark matter. And if I divide the two power spectra, I can determine the ratio of the biases without cosmic variance. Now, if I just go back to this slide here, you can see that, say, the terms in blue here can be written as an effective bias because it's something multiplying D. And the first term, B dot D, that's the standard bias. And if there's primordial non-Gaussianity, that gets changed to B plus delta B. So the bias that if we think of everything times D as the bias, then taking the ratio of the two power spectra allows us to determine the ratio of those two biases to high accuracy. And so I'll show in my last slide here what happens when we use the multi-tracer method to look at the errors on FNL, the dotted curves, and to look at the parameter for detection or not of the GR effects, the horizon scale GR effects. What you see here is the red and blue curves correspond to the single tracer case. So the blue curve is SKA Phase 1 intensity mapping survey. On its own, you can see that the error on FNL is not able to go below 1. It's of the order of 3 or 4. Similarly, for the photometric galaxy survey of Euclid or of LSST, with one tracer, you're not able to push the error on FNL below 1. And also, if you look at the solid red and blue curves, you have to get this FGR below 1 for a detection. And you can see that you can't do that with a single tracer. The black curves show what happens with a multi-tracer. So in the case of FNL, as you reduce the noise, the error goes down. In the case of the single tracer, when you reduce the noise, the error is not going down because of cosmic variance. But the multi-tracer, the error goes down because cosmic variance is being removed by this method. The solid curve shows you how well we can detect the GR effects from the multi-tracer to very high signal to noise. So I'm going to end there just by showing you the conclusion slide, and I'm sorry that I've got up to almost 4 o'clock, but if you want to ask questions, I'm happy to stick around for a while. Thank you.
Thank you, Roy. So I think I had time for questions. So any questions? Okay, so I have one question. Okay, go ahead.
Hi, Ron. Since this survey is supposed to happen with H1 band, it has some difference from regular optical surveys. for example, the optical surveys, we get red and blue galaxies, passive and star-forming galaxies. That they have different amount of H1. Can you comment a little bit in potential biases led by the H1 choice for the survey in terms of detecting, for example, higher density regions where the galaxies are supposed to have less amount of gas than filled galaxies?
Yes, so what you're asking is the question of how do you model the bias of H1 galaxies, given that you've got these odd properties, like in the high density regions, the temperature goes up, so you're going to get less neutral hydrogen, for example, especially if you're near the center of clusters. So that is an issue, and there are a lot of simulations that are being done and have been done to model the galaxy bias, the H1 galaxy bias. Probably modeling the optical bias is more advanced than modeling the H1 bias because it's been going on for longer. But in a sense, it's the same game, except that there are more complications because you need to incorporate the gas dynamics as well as just the total baryonic mass. So ultimately, bias to me is the biggest problem in all of galaxy survey cosmology, because we really don't know the bias well in any case. So there are techniques to determine the bias. If you use a weak lensing survey and a number count survey, that's one way of getting the bias. I'm not sure what other ways there might be. Oh yes, the other thing is that you marginalize over the bias. You don't assume that you know the bias from simulations. You leave the bias as an unknown in each bin, and then you do your forecasts that way. That's possible, but of course it degrades your precision. But when you've got higher and higher numbers of galaxies, that becomes more and more feasible as well. That in the future, you may even be able to get away with not knowing the bias. You'll be able to determine it from the high statistics, just throwing it in as another unknown. But you are right that the question of H1 bias is more complex because it has to tackle the gas dynamics a bit more carefully. So there is a lot of effort going into modeling that. The current models of H1 bias are definitely going to get improved. Yeah, I don't know if I've answered the question.
Well, okay, it's okay. Thank you.
And in fact, you mentioned red and blue galaxies. So in the LSST survey, you can actually separate out two populations of galaxies and use the multi-tracer method within LSST, which is a very nice feature of the LSST survey. You don't have that possibility with the Euclid's H-alpha survey because it's just one kind of galaxy, H-alpha. And you don't have it with the SKA surveys, but you do have it with LSST. So some surveys you can use the multi-tracer within the same survey.
In order to help clear the things up. Okay, thank you.
Okay, we have more time for questions. Do you have any questions? Okay, so I have a question. Could you discuss a little more about the bias definition in the synchronous gauge? Why should it be in the synchronous?
Okay. Thanks, Vinicius. Yeah, that's a good question. I went over that fast. So I think the point is the following. If we're looking on linear scales, which are large scales where we can ignore nonlinearities, we know from simulations that the velocity of galaxies and the velocity of dark matter are equal. And as you go to larger and larger scales, that becomes more and more accurately true. So if we have various halo models and peak background split models and excursion set models for trying to analyze bias. But basically the simplest case is on large linear scales where the velocity bias is 1, so they've got the same velocity in galaxy dark matter. And the simplest model is telling us that where there's a heavy enough halo, there'll be a galaxy bang in the middle of it. And so that leads on large scales to the consequence that the galaxy over density is equal to the bias times the matter over density, the halo, the cold dark matter over density, where the bias factor is independent of scale. It's a constant, or a function of redshift. So when someone tells you delta G is B times delta M, you could ask, well, what gauge are you talking about? Because if I change the gauge, that relationship changes. So why is this not a problem with current surveys? Well, with current surveys, we don't even get to the equality scale. We don't get anywhere near the horizon scale. So the difference in the gauges doesn't make any difference. Even you choose any gauge you like, as long as it's not a very weird gauge, that model for bias delta G is B delta M is going to be okay. But as soon as you go to scales that go past the equality scale and approach the horizon scale, if you change your gauge, then you're going to change your meaning of delta, and you're going to change that relationship. So then you have to ask the question, what is the physical meaning of delta G equals B times delta matter? And you can look at this various ways. The most simple-minded way is to say that in the rest frame of the galaxies, which is the same as the rest frame of the halos, that is the frame in which the two overdensities are proportional, independent of scale. So in order to get the correct bias definition, the easiest way is to impose that proportionality property in the co-moving frame. Because you know in the co-moving frame, that's where the physical meaning holds. You want the two overdensities to be proportional when you are sitting on the galaxy or on the dark matter halo, which are not moving relative to each other. So you're in the galaxy frame, or you're in the cold dark matter frame, which is the same frame. And when you're there moving with the galaxy and with the halo, that's when their overdensities are proportional. So if you make that definition for the co-moving density, which is in the synchronous gauge, if you like, then you can be sure that when you change to another gauge, the physical content will carry through.
Okay.
There are more sophisticated ways of proving that, but yeah, I don't know if that's okay for an answer.
Okay, thank you very much. And I have one more question. So let's suppose we measured the GR effects on the largest scales. Do you have an idea of what we'll be able to say about modified gravity, or have some kind of forecast?
Yes, that's a good question. Thanks. I didn't have time to mention that, but I've gone to the slide with those with those GR effects shown in the blue box. So what I didn't mention is that in the blue, this formula that I showed does not depend on GR. So if we have a modified gravity theory, which is a relativistic theory of gravity, a metric theory, then this formula will be exactly the same in that modified gravity theory. So we can actually apply this formula to include modified gravity theory. So we can use this formula, therefore, to test GR. So for example, if I don't assume that psi and phi are equal, the two potentials, as they are in GR in the simplest case, then in principle, if I can measure phi and psi from the blue box, I can test whether or not they're equal. So I can perform that standard test of modified gravity, or GR, but on the very largest scales. That test can be done using weak lensing, but that's on smaller scales. So here you can do the same test of are the potentials equal, but now you're doing it on very large scales.
Okay, thank you. So, any other question? Okay, so Roy, thank you again. It was a very nice talk. Thank you very much.
Thank you, Vinicius. It was a pleasure. I hope it was okay. Sorry about those slides in the beginning.
No, it was nice. No problem. Thank you.
Okay, great.
Bye-bye, everyone.
Obrigado. And, everybody. Thank you.